Hello and welcome. In this video, I'm going to show you how to blink an LED using the ATmega328 assembly language. Introduction. Now, this is the main program or the main code that I'll be using to demonstrate how to blink an LED. So this part of the code that is in the red dotted box is the main program, and here at the bottom here, this is the what we call the delay subroutine. Now the delay subroutine is necessary in this program because we need to slow down the microcontroller so that we can see the blinking effect. So I've extracted the main program out, and there's one instruction that I would like to highlight because a lot of the a number of the instructions here you might be familiar with it because I've used them in my previous videos. Now there's one instruction that I've not used before, that is the CBI instruction, which is highlighted here. Now I'll come back to this in a few moments. Now this is the call to subroutine, and here is another call to the subroutine. I'll get back to the delay subroutine details later on in the video. So let's take a closer look at the CBI instruction. So CBI stands for clear bit in an I/O register. So the format is here. So it's CBI. Again, let me just reiterate that this CBI can be uppercase, lowercase. It's not case sensitive. So CBI A, B. Now A is a register from ranges from 0 to 31. So this could be register 0, register 1, register 2, and so on. So it's between 0 to 31. Now the B is the bit in that particular register. So the bit could have a value of 0 through to 7. So it could be bit 0, bit 1, bit 2, and so on. And the maximum is bit 7, which is the 8th bit. So here I've highlighted the CBI instruction again. So in this case, if you notice, the I/O register is port B, and the bit that we are interested in port B is bit 0. So with this instruction, CBI port B, 0, that would clear bit 0 of port B. That means port B bit 0 will be set to a logic 0. Okay, so next I would like to take a look at into the details of the delay subroutine. Now, before I get into the details of the delay subroutine, let's take a brief look at what is a subroutine. Now, a subroutine is a sequence or a group of instructions that is written just once, but executed when it is needed by the main program. Let's see how this works out with this diagram here. So here I have representing a main program with some instructions, and there is a call to a delay subroutine. All right, this call is a ATmega328 instruction. So here it will call a subroutine called a delay. So that when this instruction is invoked or called, it will then leave this main program and execute a subroutine. And there may be several instructions in the subroutine depending how long the subroutine is. Once the subroutine has been executed or completed, the last instruction of a subroutine is an RET. That is the return to the main program, or the subroutine will hand the control back to the main program. Basically, that's how a subroutine works out in a program. All right, so I've extracted again here the main portion of the main program of our example, and I just like to highlight the call to the delay subroutine, which is this one, the instruction here, and the other call is here. So let's take a look at the call instruction. Basically, this is a ATmega328 assembly instruction. You will find similar instructions in many of the other types of microprocessor or microcontroller. It is quite a common instruction. But for the ATmega328, this is a long call to the subroutine. What this means is when this is executed, K actually represents the range of memory addresses that it can reach out to. So for the ATmega328, the call can call a subroutine within address 0 all the way up to 64K of addresses. That's how far it can reach for a subroutine. But notice in our code or program, the call uses a label rather than an address. Now, in this case, delay, the label delay points to the start of the subroutine, and this is quite common. Okay, now let's take a look at the delay subroutine that is being used in our video. Now, this is the delay subroutine that I'm going to use, and I'm going to get into the details of this subroutine now. Now, before I actually get into the details of the subroutine, let me just take a look at something called a single loop. Now, the single loop, the flow chart for the single loop is shown here, and here is the code of using the ATmega328 assembly code to implement this loop. Basically, what this single loop would do is to set up a counter. Now, the counter will be given some initial value, as is shown here, LDI R21. So R21 would be the counter. This can be any other register. It doesn't have to be R21. And so the initial value is 255. So we go back to this flow chart here. So we decrement the counter by 1. I mean, subtract it by 1. And then ask the question, is the contents of the counter 0? If it's not 0, go back and subtract or decrement the counter by 1 again. Now this will go on for a little while until the contents of R21 is equal to 0. When that happens, the loop will end and it comes out of the loop. And basically, this is how it's been implemented. So you decrement R21 and subtract 1 from it, check it. Is R21 equal to 0? If it's not, go back and do it again. So this BRNE loop 1 will go back here. So this will go on for a while until R21, which is the counter, is the contents of R21 is 0. It will then exit this loop and ends the loop. Now there's two instructions here that I want to take a closer look. That is the DEC and the BRNE instruction. So first off, let's look at the BRNE. BRNE stands for branch if not equal. So BRNE, this is the format. and K, although K in our program is a label. So K is actually the offset. That you can have the offset of -64 or all the way to +63. Basically, these are the number of locations. There's no such thing as the minus location, but what it means is a backward branch or backward jump. This is a forward jump. So this is the number of location it can jump to. So now to simplify this thing, I've used label instead of using these values here. All right, as you have seen it in our example. The next one, as explained earlier, is the DAG. Basically, this subtract 1 from the register. In this case, the register that we have used in the example is 21. So D is the number of the register. So this could be from register 0 all the way up to register 31. And our example, as I'm repeating here, is the we have used R21. Okay, so we are in the ATmega Studio 7, and I've created a new project to demonstrate the single loop function. So here I have the code. I have slightly modified the code in that the setup, during the setup counter, I've only giving a 3 to the counter, which is register R21, and then that's the only modification that I made. So let's build the solution. Right, so it's successful. There's no errors. Now let's go to debug and start the debugging session. Now for this, let me just close this in for now. For this, we need to go to debug. To Windows, and then look for processor status. Click on that, and we have the processor status. We scroll down until we see the status register. All right, there are several bits or several flags. I'm only interested in this flag here, the Z flag. Right, so we've got everything set up. We got the registers, and right now register 21 is 00 hexa. So let's go through the program. So the first thing, and I'm going to single step, is to execute this instruction here. Now we should watch R21, which is this one here. All right. So watch R21. We have 03. So because that's what we have instructed the program to do, copy this value into R21. So we have in R21 03. And now the second instruction will subtract 1 from R21, so we should expect to see a 02 here. Let's see if we are right. Yes, it's a 02 in R21. Then this BRNE instruction will check is the contents of R21 0 yet. All right, if it's not 0, we need to go back to this point here, loop. So let's see if it does that. It does. So now R21, as you notice, is 02. So we subtract 1 from it again. So it's 01. Ask the question, is it 0 yet? It's not. Go back. All right, we go back. Yeah, and we go back. And this time we're going to subtract another 1. But this time, watch R21. We should see a 0. Yes, it's 00. Ask the question, is R21 0? Yes, you should come out of this from this loop. You should come out from this loop and go down here. Let's see if it does that. And watch out for the status register now. Notice the status register now is highlighted in red, the Z flag, indicating that the result is 0. So now it should come out of this loop and come down to this part here. All right, let's see if it does that. Yep, and it does. Now, quite often, the single loop may not be sufficient. And this is because microcontroller or microprocessor, they operate in the megahertz range. So this is way too fast for the human eye to see. So we need to turn our attention for nested loops. Now, nested loops are also known as a loop within a loop. So here is an example. I have two counters, outer loop and the inner loop. Let's take a bit of closer look at the so-called inner loop. If you notice, the inner loop is the single loop that we have just looked at earlier. So in the inner loop counter, which is R21, we give it a value, decrement that counter by 1. If it's not 0, go back and do it. So it will do it 255 times decimal. Once this is done, it comes out and it will then decrement this second, this outer loop counter, which is being set up here with the initial value of 255. So it would subtract 1 from the R22 and then ask the question, is it 0 yet? If it's not 0, if R22 is not 0, go back to loop 2. Now, look at loop 2. Loop 2 will then reset R21, which is the inner loop counter, with a value of 255, and then this repeats again, 255 times decimal. And then it comes, when this is done, it comes out and then it subtract 1 from R22, ask the question, is it 0 yet? Is R22 0 yet? If not, go back, repeat this again. All right, so let me highlight this outer loop. So now we have a loop that is within another loop. All right, so this inner loop here will be repeated as many times, determined by the value of the outer loop. Right, we are in the ATmega Studio 7, and this time what I want to do is to demonstrate the double loop or the nested loop, the loop within the loop program. So I've uploaded the program here. So let's go to build and build the solution, and there are no errors. It's successful. So the next thing we need to do is go to debug. All right, so now it's in debug mode. Now there's two panels here that we need, the register panel and also the status, the processor status. And in the processor status, we look for the status register, all right, which is this row here. Switch back to the register panel first. So quick look. So we've got two counters here. R22 is for the outer loop. R21 is for the inner loop, which is this one here. All right, so let's start out with the first counter for the outer loop. So let's see, load decimal 2 to R20, register R22. Yes, so R22 is here and it's now got 02. Next one is to load 2 into R21, which is this one here. All right, now right now it's 00. Yes, it's got 02, which is good. Now the next instruction will decrement or -1 for R21. So watch R21. It's now 01. That's correct. And then it comes to this checkpoint here, which asks, is the contents of R21 equals to 0? No, it's not. So it will go back to loop 1, which is this one here. All right, so yes, and it will decrement R21. R21 at the moment is 0, 1. All right, so now it's 0, 0. And if you go to the processor status, look at the status register, the Z flag is red. That means it's set to 1, indicating the result is 0. So a 1, Z equals to 1 means there is the result is 0. Right, so now it will come out this loop, drop down to the next instruction, which is this one here. All right, so let's do that. Right. Now, R22 at this moment, it has a value of 0, 2. So we decrement that. Yep, it's gone to a 1. Is R22 0 yet? No. So it will go back to loop 2, reload R21 with 2, because right now R21 is 0, 0. All right, so watch R21. Yes, it's reload with 2. So next instruction decrements it by 1. Is R21 0 yet? No, not yet. Go back and subtract 1 again, or decrement 1 from R21. And watch out for R21 here. All right. Before we do that, let's look at the status register, right? The status register Z flag is now 0. It's clear. So let's see what happens. Now we take 1 away from, and now it's 0, 0. R21 is 0, 0. Let's go to this process, and you see the Z flag is set to 1, telling us that the result is a 0. So now it drops down to the next instruction. All right, now R22, it's in a moment 0, 1, and the status register is still not clear yet, but watch out when I execute this one. R22 is 0, and the status register is still set to a 1. So it says is 22 equals to 0? The answer is yes. So it comes down and the whole thing ends. All right, so this is how the nested loop works. Now, sometimes even with a double loop, as we've seen before, a loop within the loop, that may not be still not enough, because, for example, the ATmega328 microcontroller operates in this at 16 megahertz. So the double loop that we have seen earlier may not be sufficient. So we need to turn to this method, or this technique, where we have this inner loop as seen earlier, which is implemented here, all right, in the ATmega328 code. And then we have the outer loop, which is in the blue box. This is the repeat of the double loop as we've seen earlier. And then on top of that, we add in another loop. All right, so this loop here will be controlled by this loop here, and this 2 loops here is controlled by this what I call the outermost loop. So this is a loop within the loop within a loop. Now this is the subroutine, delay subroutine that we are using in our example here. So I've repeating the code here to complete the explanation. So we have the main program here. All right, the main program here, and this first 2 lines basically set port B to output mode, and then this will set port B bit 0 to a 1, call the delay. When the delay is complete, it will clear bit 0 of port B. Let me set it to off state, call the delay again, and then when that is done, it comes back here. When it says R jump main, goes back, switch the LED on, call the delay, clear the bit 0, call the delay, and then jump back, set the bit 0 to 1 again, and it just keep repeating, and we will get a blinking LED on port B bit 0. Right. To test the program or the code, we require some hardware. And here's the circuit for the interface to the Arduino Uno. Basically, it consists of a 220 ohm resistor, and one end of the 220 ohm resistor is connected to pin 8 of the Arduino Uno, which is this one here. And pin 8 is basically port B and bit 0 of the ATmega328 microcontroller. The other side of the resistor, which is this part here, that's connected to the anode of the LED. And the cathode of the LED, which is this part here, is connected to ground of the Arduino Uno. And basically here is the wiring diagram for this schematic here. Here is a picture of the actual setup. As you can see, there's the red LED. It doesn't have to be red, it could be any color of your choice. There's the 220 ohm resistor, and it's connected to pin 8 of the Arduino Uno, and this black wire here connects to ground of the Arduino Uno. Okay, so we are back into the ATmega Studio 7, and I've uploaded the complete code that will blink the LED. So this is basically a copy of the code that we have been discussing in earlier. So let me just build the solution, and it's successful. There's no errors. So now what we're going to do is we're going to upload it to the hardware and see if the thing works. Now, before we do that, let me just try and set up the hardware and get the camera to focus on it. Just give me a minute. All right, so here we have the code here and the hardware setup. So let's go to Tools, and let's upload the program to the Arduino Uno. Yeah, and as you can see, now the LED is blinking. Let me just see if we can focus it better on this thing. Sorry, the video cam for the video cam quality, but as you can see, the LED is now blinking. So the thing is working. Hey, so we have come to an end to this video. I hope you have found this video useful, and I'd like to thank you for watching, and I'll see you in the next video. Bye.